Good morning, this is Dr. Raj Kumar Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain the upward flow in a plane narrow slit. So this is the narrow slit is where the distance between the two plates is 2b, and width is very large as compared to the distance between the two plates, and length is again very large than width actually. Flow is upwards by applying a pressure gradient here. So you have pressure at the inlet is P1, pressure at the outlet is P2. G is acting vertically downwards, so direction of flow is being considered as X. Z direction is considered along the width of the plate, and Y direction is perpendicular to the plates. So at steady state, del U upon del T terms is 0, and steady unidirectional flow in X direction only. So V and W are 0. Fully developed flow in X direction, so del U upon del X term is 0. Newtonian flow is tau by X equal to mu del U upon del Y. So if we apply the X momentum balance, which is the direction of the flow, this first term is getting cancelled due to steady state operations. Second term del U upon del X is getting cancelled due to fully developed flow in X direction. V and W are getting cancelled because flow is totally one dimensional in X. Here this term is getting cancelled due to fully developed flow in X directions. Now del U upon del Z term is much more lower than del U upon del Y. Therefore this term is getting cancelled based on the magnitudes. Because the dimension is Z axis is extremely large as compared to the dimensions in Y. So the resultant equation is that 0 equal to rho gx minus del P upon del X plus mu del square U upon del Y square. So we can write here that del square U upon del Y square minus rho gx plus del P upon del X, and considering delta P equal to minus rho gx upon del P upon del X. So delta P is modified pressure here, so we can integrate it, so we will get a constant here C1. Then again integrating this, we will get U del P upon mu Y square upon 2 C1 by plus C2. Now boundary conditions at y equal to plus minus b, velocity equal to 0, no slip conditions, so we can apply that. At y equal to 0, one equation is this one, then another this. Adding both the equations, we will get a constant C2. C2 is minus delta P upon 2 mu b square, and then substitute C2 is equation 3, then you will get your constant C1, which comes out to be 0. So hence the velocity expression is delta P, this one, the delta P dash b square upon 2 mu, then minus here, this is minus here, so 1 minus of y upon b square. So this we can write in this particular format here, this one. For horizontal plane, that gx is equal to 0, so del P upon del X equal to delta P by L. So we can write delta P by 2 mu L b square 1 minus y square upon b. Now for vertical, that gx is minus g, so delta P equal to minus rho g delta P by L. So this we can write here that rho g plus delta P by L b square upon 2 mu L 1 minus y upon b square. Volumetric flow rate, Q is V dot dA, so U dot dA, so we multiply U. dA is dy into dz, so y is changing minus b to b and z is 0 to w. So we integrate this and then substitute the limit. So we will end up with this equations here for V by 3. Final equations for volumetric flow rate is minus 2 by 3 delta P dash B cube W upon mu. So for vertical case, delta P dash is minus rho gx plus del P upon del x. So gx is minus g, so this rho g, you get rho g minus delta P by L. Q comes out to be 2 by 3 delta P by L rho g B cube W by mu. So this is about the upward flow in a plane narrow slits. Thank you.